Good morning, friends. It's time to begin the class. A couple of announcements. We have a lecture this Saturday. So this is lecture 12. Lecture 13 will happen as per schedule on Thursday, but lecture 14, the next one, will happen this Saturday. Saturday is a buffer day, so we'll utilize it, and during the regular lecture time, we'll have a lecture. Okay, so we don't have a minor exam, so that's probably a good news for most of you. One more announcement I wanted to make is, in spite of giving clear instructions, we do have some homework submissions in which answers have been either copied from the internet or from one another. So my plan is to give you a chance to withdraw your homeworks in case you have done that, right? So if you withdraw your homework, you just get a 0 and that is the end of the story, 0 in the current homework. If you don't withdraw and we find that you have copied it from somewhere, either from the internet or from somebody else, then the academic dishonesty policy will be applicable. Yeah, so I hope none of you who is present over here has done that. So this is really for people who are not present over here in that case. Okay, I will also make an announcement. Yeah.
Yes, sir. Excuse me, sir. So we are starting with a minus on 19th. So is it possible that we could postpone lecture 14 for some time?
Okay.
Yes, sir.
So sorry.
Yeah, I think the same thing.
Yeah, I see. So I heard you have two minor exams on September 19. Is that true?
Yes,
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
Okay. Okay. And totally how many minor exams do you have? So this course does not have a minor exam. So Sunday takes care of two exams. How many more exams do you have?
So two
Sir,
more.
most of
seven
us have 6 total.
Sir, till 23rd. So from 24th, probably we'll not have it.
Wait. So 24th. But 25th we are already using that buffer day anyways. 25th of September. So what I would suggest is so how about this? So you'll get done with two of your minors on 19th. On 20th, in the minor exam slot, we'll have a lecture. Does that work? Right? So my proposal is we could change this to September 18 to September, whatever that date is. I think it's 28th. So our minor exam slot, the minor exam slot given to us is September 20 and it is supposed to end at 11, right? The B slot minor exam, right? So we'll have the lecture on September 20 in this time. Is that fine?
Sir, is it possible on 25th, 24th, that is a Friday, like we had extra tutorial this Friday, we could have something during that time as well?
Extra tutorial. Well, so there was no guarantee that everybody would be able to attend it in anyways, right? So for that, I had given an option to kind of ping me at any time and ask your questions. So that I cannot be sure, right? Because you remember, right? So when we tried to figure out what should be our tutorial slot, there was a big discussion, and then we had a hard time figuring out one slot.
Yes, sir.
Right. So let's take a vote. Let's take a vote. There are 56 people in
Sir,
class.
I think 24th should be a holiday for us because it's just the next day after minors. So
No, it's not.
I don't think it's a holiday.
Okay.
Yeah. So let's vote. Okay. So we have 56 people in class. How many of you raise your hand if you want if you prefer a lecture on September 20? Okay, and then everybody who does not raise a hand, I'll assume that they prefer September 18. Raise your hand if you prefer September 20.
So we have option between 20 and 18.
Yes. Raise your hand if you want it on September 20. Keep it lowered if you want it on September 18. Okay, let's see. So there are 56 people. I hope everybody who wants to raise their hand has raised their hand. So I can start counting now. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Yeah, around 35, maybe slightly more than 35 people who have raised their hand. So that is the majority. Okay, fine. So we'll make it September 20. Cool. Okay, you can lower your hand now. Okay, let us quickly recap the couple of definitions we did in the last class because we are going to continue that discussion. Right, so we defined the notion of a bipartite graph. We said that a graph is bipartite if you can split its vertex set into two parts so that every edge has one endpoint in one part and the other endpoint in the other part. Right, so then we defined this notion of a matching in an arbitrary graph, not necessarily bipartite. It's just a subset of edges such that no two of them share an endpoint. Okay, no two of them are kind of adjacent. Well, we talk about adjacent vertices. Usually we will not call edges adjacent, but yeah, if that makes sense in your mind, then yes, that's what we mean. Okay, so this is one definition, little definition that I'm adding to this. So we call a matching M to be a perfect matching, right? So if for every vertex there is an edge with endpoint V, right? So if you have a vertex, let's say you have 6 vertices, then something like this will be a perfect matching. Okay, so every vertex is kind of covered by an edge, by a unique edge, obviously. Okay, and then why did we look at these notions? The problem that we are trying to solve is the following, right? So you have several students and you have several rooms, and each student has given a subset of has specified a subset of room which they are willing to accept. Okay, so that is indicated by an edge. And now the questions that we are asking is, can we accommodate all students? What is the maximum number of students that we can accommodate, and so on, right? So we looked at this, right? So in this diagram, we noted firstly that there is a perfect matching, right? So Aman is given room 1, Riya room 3, and so on. So this is a perfect matching. But the question we asked is, how do you compute a perfect matching, or how do you compute a matching of maximum possible size? Okay. And then we said that the plan is the following. Let's start with the empty matching. The empty set is obviously empty set of edges is obviously a matching, right? And then successively we'll make sure that our matching size increases by 1 in every iteration somehow. Okay, we are yet to prove that that gives us a maximum cardinality matching, but let's understand that idea first, right? So suppose our current matching is the set of red edges, right? So what did we say? So we said that, okay, under this situation, we could ask maybe Kushagra to occupy room 2, but room 2 is already occupied by Aman. So we'll ask Aman to shift from, come out from room 2, vacate room 2 and occupy room 4. Room 4 is already occupied by Isha, so we can request her to vacate room 4 and assign her room 5. Okay, so that from a matching of size 3, this way you will get a matching of size 4. Okay, Sthiti Pradnya, you have a question? Sthiti Pradnya Sahu, your hand is up.
Sorry, sir, I forgot to lower it.
Okay, so cool. So this kind of a path, right? So which starts from an unmatched vertex, right, and traverses the non-matching and the matching edges alternately, and also ends in an unmatched vertex. We call such a path an augmenting path, right? So this is what we also defined in the last class. We said that, right? So if you have a bipartite graph and you have matching M, right? So an alternating path of M is a path which has edges alternating in M and not in M. Okay, so any such path is called an alternating path. Similarly, an alternating cycle is a cycle in which the edges are alternately in M and not in M. Remember, since G is a bipartite graph, the length of every cycle is going to be even, right? So therefore, it makes sense to have a cycle. I mean, yeah. Therefore, this notion makes sense, right? So alternate edges are in the matching and not in the matching. And then more importantly, we said that an alternating path of M is called an augmenting path. When do you say it is an augmenting path? If the first and last edges of that path are both not in M. Okay, so which means that which means that an augmenting path has necessarily an odd length, and just because the graph is a bipartite graph, the alternating cycle also has an even length. In fact, every cycle has an even length. Okay, is everybody with me up to this point? Raise your hand if something is not clear so far. Actually, let us quickly see some alternating paths over here, right? So this is an augmenting path, which is also an alternating path. If I just take a prefix of this path, let's say Kushagra R2, Aman R4. Well, even that is an alternating path, but not an augmenting path. Right. Oh, sorry. Wait. Sorry, my mistake. I should have said an alternating path of M is called an augmenting path of M if the first and the last, sorry, my bad, last vertices are not matched. Matched. Right. So first and the last vertices should be unmatched. Sorry for that. Right. So which is why Aman R4 Isha R5 is not an augmenting path. We want the first and the last vertices to be unmatched necessarily. Okay, any issues up to this point? Yeah, I made this mistake even in the last class, so I'll fix even those lecture notes and upload them once again. Yeah, Shrivanti?
So then the matching that you have done, it is not an augmenting path.
Sorry?
So how can Kushagra remain unmatched? Like Kushagra will be matched to R2, no?
No. In the current matching, if you consider the set of red edges, that's a matching, right, Shrivanti?
Yes, sir.
Yeah. So now the question is, how can we improve it? Right. So what we did was we started out with an unmatched vertex and figured out an augmenting path. What is an augmenting path? It's an alternating path, right? So where edges are alternately not in M and in M, and the path also ends in a vertex which is unmatched, right? So this path starts from an unmatched vertex. Kushagra did not have a room. Okay.
Sure.
Yeah, and R5, nobody occupied R5 earlier. Right, so which is why R5 was also unmatched. So this path starts from an unmatched vertex, ends in an unmatched vertex, and it is an alternating path. So we'll call this an augmenting path. Right, and the reason why we are looking at augmenting paths is the augmenting paths let us improve our matching in some sense. Right, so if I take a matching and XOR it with the set of edges traversed by an augmenting path, I'll get a better matching.
So, like, what was the difference between the definition you wrote earlier and I'm not getting it?
Earlier by mistake I said that the first and the last edge must be a green edge, which would also have made Aman R4 Isha an augmenting path. Aman R4 Isha R5, but that I don't want it to be an augmenting path because that is completely useless as far as improving the matching is concerned. No? Aman R4 Isha R5, right? So it's a path of length 3. First edge is unmatched, second edge is matched, third edge is unmatched. But that is not going to let us improve our matching. Okay, so we need to start from an unmatched vertex and also end in an unmatched vertex. Okay?
Yes, sir.
All right. So now what? Yeah. Right, so observation. What is the observation? If, yeah, right, so let M be a matching in a bipartite graph, or well, yeah, okay, fine, bipartite graph and let P be the set of edges traversed by an augmenting path of M. Right, so what am I talking about in this diagram? So let M here really refers to the red matching, and P refers to this set of edges, right? So this P for us, and the red is, this is M. Okay, so M is a matching in the bipartite graph. Let P be the set of edges traversed by an augmenting path of M. Then what? Then we want to say that M symmetric difference P. I hope you remember the symmetric difference operation, right? M is a set of edges, P is a set of edges, right? So this, I claim that this is a matching, and furthermore it is a better matching than M, right? So size of the set M XOR P is greater than right, so in fact it is size of M plus 1. So let me make it explicit. Raise your hand if you think you will be able to prove this on your own.
So what was the symmetric difference you said?
So symmetric difference of two sets is, yeah, you have this one set, you have this other set, right? So this A, this B. Then A symmetric difference B is this set. The set of elements which belong to exactly one of A and B.
Okay.
Yeah. Okay. So what should we do? Should we take this as a tutorial problem, right? So it's kind of, yeah, just stare at the diagram and the proof should be easy, right? So two things you need to prove over here. Right. So I'll add this as a tutorial problem, and if something is not clear, we'll discuss it in the tutorial. Okay. So I hope that is fine. Okay. So we'll take this to the tutorial. Let me just mark this so that I remember. Oh, by the way, raise your hand if the definition of augmenting path is not clear. If that is the reason you are not sure you'll be able to do this, let's get that out of our way. Raise your hand if the definition of augmenting path is not clear. Viraj, any specific question you have? What part is exactly not clear?
Like, just could you just tell once again, because I'm not 100% clear about it. Nothing specific. I'm just not.
Okay. Yeah, I'll do that. Rishabh?
Sir, same, sir.
Prabal, your hand was also up.
Sir, I understand the definition, but how does it relate to this?
Relate to
Sir, the symmetric difference.
Oh, acha. Okay, fine. So let's work out this example. Okay, let's see what happens in this example, right? So your M, right? So this is the perfect matching here. This is what you're trying to reach, right? So your M over here, your current M over here is the matching, right? So Aman R2. Guys, could you mute yourself? I'm getting noise from somebody. Okay, Aman R2. Shrimanti, I can see your hand up. I'll come to you. What? Isha R4 and Riya R3. Right. So this is the matching. And this, what is this path? Right. So what are the edges traversed by this path? So you are taking the XOR of this matching with the edges traversed by this path. What are the edges traversed by this path? Kushagra R2. Then Aman R2. I'm just kind of reorienting the edges. Aman R4, Isha R4, and Isha R5. Okay, so suppose I do an XOR of these, what happens, right? So Ria R3 will remain, right? So M XOR P, right? So Ria is not participating in this path at all. So Ria R3 will remain, right? So what happens to this edge Aman R2? Aman R2 is present over here. It is present in the original matching and it is also present in the augmenting path, Aman R2. So that will disappear. Okay, so let's do it. Okay, sorry. So let's do it this way. So Kushagra R2 is present in the augmenting path, but not in the matching, right? So that is going to be present in M XOR P. Right? But now the second edge Aman R2 is present in both. So that is going to disappear. Right? So that has the effect of sending Kushagra into the room R2 and asking Aman to vacate room R2. Okay. What about the next edge? So Aman R4 is present in the path but not in the matching. Well, so that amounts to assigning room R4 to Aman. But Isha R4 is present in both the original matching as well as in the path. Right? So that edge is going to disappear, which means we are requesting Isha to vacate the room. Right? And finally, what is happening? So Isha R5 is present in the path but not in the matching. Fine. So Isha R5 comes in M XOR P. Right? So this becomes our new matching and its size is one more than the original matching. Okay. Arin?
Sir, I had a doubt regarding definition of augmenting path.
You had a doubt in the definition of augmenting paths. Okay. Yeah, go on.
So what do we exactly mean by the first vertex and the last vertex are unmatched? Do we mean that the certain edge is not present in the current matching, or that edge is not present at all?
Unmatched vertex is a vertex which does not, it's a vertex such that no edge incident on that vertex is in the matching.
So sir, why? Okay, so Kushagra R2 and Aman R4, why is it
Kushagra R2, Aman R4, why is it
why is it not an augmenting path?
Because R4 is matched, no? R4 is already matched.
Okay, sir, got it. Okay.
Right? So we are saying that the endpoints of this path should not have a red edge.
Okay, sir.
Right? Only then you can improve, right? You need to find a person who is not given a room, and you need to be able to find some room which is available. And somehow they should be kind of reachable from each other in a specific manner, and that specific manner is an augmenting path.
Okay, sir.
Right? So you should be able to put the student in some room, ask the student already in that room to vacate the room, put that student in some other room, and so on, and eventually get a student into a originally vacant room. Then you have improved your allocation. Right?
Okay, sir. Okay.
Yeah. So that is the idea. Okay. Yeah. So we are going to leave this for the tutorial. Now, okay. Yeah. So Shrivanti, your hand was up.
So it got resolved.
Okay, so there are some people who did not understand, I think Vedant or I don't know, I forgot the names now, who were still not sure about the notion of augmenting paths.
Understood after this example.
Okay, awesome, good. Any more questions? Yeah, I'll wait for a couple of seconds maybe. Okay, so right, so what do we know? So what does this imply? Right, so therefore another observation, right? So this second observation should be trivial if you assume the first observation. If a matching has an augmenting path, then it is not a maximum size matching. Right? So what do I mean by that? I just mean that there exists another matching in the graph with size strictly more than the size of this current matching. And what is that matching? That matching is just M XOR P, right? That is one such matching. There could be several others. Abhinav?
Sir, you said that a matching has an augmenting path. So how does this augmenting path belong to matching M?
I never said that.
How can an augmenting
I
no
never
here
said
in
that.
observation, if a matching M has an augmenting path,
Huh.
so can an augmenting path belong to a matching?
No, that's not what I'm saying. An alternating path of M is called an augmenting path of M, right? So this is the way we defined it, right?
Oh, okay.
Called it an augmenting path of the matching, right? So if the matching has an augmenting path, I'm not saying the matching contains an augmenting path or an augmenting path is a subset of the matching. That's not what I'm saying.
Okay.
Yeah, so if a matching has an augmenting path, what do? You just XOR the matching with the edges in the augmenting path and you get a better matching. Right? So therefore the original matching is not a maximum size matching. Okay, so this gives us some recipe. It gives us some recipe of improving the matching successively, right? Start from an empty matching, find an augmenting path, XOR it, find another augmenting path, XOR it, find another augmenting path, XOR it, and so on. Right? So as long as you are able to find augmenting paths, you will keep on XORing, but at some moment, let's say you fail to find an augmenting path. You have some matching which does not have an augmenting path. Now what? Can you safely claim that this is a maximum matching, or there is some completely different matching which is strictly larger than this? Is that possible? Okay. So do you understand the question? Why do you actually reach a maximum?
I think that would. Arun.
I think we can prove that if a matching doesn't have an augmenting path, then it has to be maximal.
Okay. Yeah, Arun, I'll come to you. I'll come to your idea. I'll ask you what idea you have in mind. Somil, your hand is up.
Yeah, I think I have an idea for it. I'll share it.
You also have an idea. Okay, fine. Chinmay?
Sir, in this, when we are like, for example, in this Kushagra to Aman, so when we come to Aman, there are like multiple edges possible, so we can take any, right? Like,
could anybody hear Chinmay?
hello, am I audible, sir?
Yeah, better.
Yes,
okay.
Chinmay is audible.
Sir, I was saying that like here when we go from Kushagra to R2, then Aman has to shift to another room, so he can shift to R4 or R1. So that choice is arbitrary, right?
Yes, that is arbitrary, right? So yeah, exactly. Correct. So good point. So observe that in this setting, right? So even Kushagra R2, Aman R1, even this is an augmenting path. Okay, we ask Kushagra to occupy room R2. R2 already has Aman in it, so we request Aman to change his room from R2 to R1, and that's the end of the story. That is also possible, right? So there could exist several augmenting paths, not just one, right? All we are saying is as soon as there exists at least one augmenting path, the matching is not the maximum. Yeah, it's not a maximum size matching. Ramanuj?
Sir, I think we can make the claim that if there does not exist an augmenting path for some already chosen people, then those people, like you cannot, even if you change the order of those people, you cannot add another person. But I don't think we can make the claim that we can always reach the maximum augmenting path by following a process.
I'm talking about maximum matching, not maximum augmenting path.
Sorry, maximum matching by following the process.
Acha, so you don't think that you might be able to find a maximum matching, right? So remember, there could be tons of maximum matchings, right? As long as we just find one of them, we are happy. Okay. So my question is, by this process, can you reach some maximum matching just by XORing with augmenting paths, repeatedly finding augmenting paths and doing an XOR? Somil, your hand is still up.
I forgot to lower it.
Okay, fine. So Arin, you said that this is a necessary and sufficient condition, right? So Arin thinks that if the matching does not have an augmenting path, then it must be the maximum size matching. Do you want to explain us why? What do you have in your mind, Arin? What is the idea?
Sir, I don't have anything concrete. I'll post it on discussion forum.
Sorry?
I'll post it on discussion forum.
Okay, so there were some other people who had some idea. Do they want to share their ideas? Yeah, Somil.
Yeah, so okay, let's say M is not the maximal matching, but it does not have any augmenting path either. Then we'll get a contradiction. So let's say M.
Sorry, so what is the plan? M is not maximum. Not maximum size matching and does not have augmenting path. Right, so you are assuming opposite of what you want to prove, and now you want to get into a contradiction. Okay, go on. How do you do that?
So let's say in the matching M, the students who were allotted a room, call that set A.
Okay,
and
so A is the set of students who have been allotted a room. Okay.
And B is the set of rooms they were allotted.
Okay, fine.
And let's say M dash is a matching with size greater than M.
Okay.
Like
large
amount. So there must be some students which were not in A but are now allotted rooms, right?
Yeah, matching of size. Yeah, let's note down a second. Of size strictly greater than size of M. Okay, yeah. So therefore, there must be a student who is allotted a room under M dash who was not allotted a room under M. Good. Okay, then what?
Let's take all those students. Let's call this set, I don't know, C.
Okay,
The
so
set of
C is the set of students who, yeah, okay, matched in M dash but not in M. Okay, so this is set C.
Okay, so now note that if a student in C was matched to a room which was not in B, then it would be an augmenting path with respect to M.
Perfect.
So
good.
that cannot happen.
Right. So if such an edge exists, then you're done. Yeah. So this is an augmenting path. Yeah. So that cannot happen. Cool. Then what?
So any student in C must be mapped to a room in B.
Okay.
So I'll just give a high level idea of what I'm going to do next. So what I'll do is I'll basically show that each student in C will displace some student in A some sense. Basically, you do the same thing when you build an augmenting path. You matched a student in C to a room in B. Then you must find a new room for the member of A which was going to the room which is now with the member of C. Then you allot it a new room. Then you end up displacing some other student in A. So you keep doing this, and you see that I can prove this, but at a high level we'll say that this process will have to end with some member of A being displaced, because if some member of A is not displaced, it would mean that some member of A is matched to a vertex other than a vertex in B, which will give us an augmenting
path. Okay, so some member of A will be displaced, then what?
And I can show that the member displaced is different for different members of C. Like two different members of C will displace two different members of A.
I see. Okay, fine. I think you have the right idea. You're just missing some small details over there, which will fill in. Raman, your hand is up. So, Amil, could you mute yourself and some background noise from you?
I have a doubt in this thing. So basically, in augmenting path, we're displacing people, but we aren't really removing anyone who has already been. We are just giving them another room.
We are just giving them another room. Yeah.
Supposedly, we start with a person who in a max who cannot be in a maximum matching set. Like we construct an example in which there's a person who possibly cannot be in a maximum matching set because he ruins everything if he's in there. Now, if we start with him and we keep doing augmenting paths, he'll always be in the set of which we are trying to create the maximum matching one, right?
Yeah, makes sense.
So now we are saying that for every person, there exists at least one maximum matching path which contains that person.
Provided that person's choice of rooms is non-empty.
Yeah,
right?
Provided that person's choice of rooms is non-empty.
Nice observation. So if we are able to prove this claim that suppose we that's nice. Okay, suppose we have managed to prove the claim that if a matching does not have an augmenting path, then it must be a maximum size matching. Then an implication would be what you said, right? So every vertex which has at least one edge incident on it is matched under some maximum matching, right? So for that vertex, there exists some maximum matching which matches this vertex, right? And the maximum matching which matches two vertices could be different. Okay, so it might not be possible to match two vertices simultaneously in a maximum matching. That is entirely possible. Yeah, Ramanuj, is that another way of stating what you said?
Yes, sir. So can we also extend this to a set of vertices which have already been matched? That set of vertices will always be in a maximal matching then?
Yeah, so you can say that. Yeah, so basically you can so what you're saying is if S is a set of vertices which can be matched, let's say S is a set of students. Let's keep the vertices on one side. If S is a set of students who can be assigned rooms in a feasible way, then there exists a maximum matching in which all students in S are assigned rooms. Yeah, that claim you'll be able to make. Yeah, you're right, Ramanuj. Very nice observation. Okay, so should we see the proof of this claim? First, let's write the claim now. Let's get rid of this. Okay. Theorem. Let G be a bipartite graph. Bipartite graph with bipartition V1, V2, right? Let M be a matching in G. Okay. So what are we trying to prove? Yeah, if M does not have an augmenting path, then M must be a maximum matching. If M does not have an augmenting path, then M is a maximum size matching in G. Yeah, so in other words, there is no matching which is strictly better than M. No matching which has size strictly larger than the size of M. Okay. Yeah, so the proof is more or less uses the same idea as what Soumil said, except that we'll focus on a specific subgraph of this graph. Okay, and how are we constructing the subgraph? We'll construct it as follows. Proof. Let M star be a maximum size matching in G. Right, so there could be several maximum size matchings in G. Just pick one of them arbitrarily. Okay, so remember here we are right. So even if we have not written it explicitly, we are using the fact that the graph is finite, and therefore the set of matchings in the graph is finite, and therefore you can find a matching which has the maximum possible size. Okay, so M star is a maximum size matching in G. Okay, so look at the graph, right? So look at the graph, right? So the vertex set is same B, right? And the edge set is going to be M union M star. Right, so what are we doing? We are keeping the same set of vertices, but we are just putting together the matchings M and M star. That's all. Okay, so now my question is, how do the connected components of this graph look like? Okay, so question. Right, so how do the connected components of this graph look like? What kind of connected component can you possibly see in this graph? Okay, any ideas? What at all can you see? Let's just make a list of what kind of connected components can this graph have.
Like all vertices which
Sorry?
are either in
Like all vertices which are part of the matchings, like belong in M or M star. I think like when we form a matching that like separates out those two vertices, right? Then they don't remain connected. That edge, those two vertices and that edge don't remain connected to the graph. Like
No, that's not what I'm saying. That's not what I'm saying. I think you are misunderstanding something. Right, so M is a set of edges, M star does not, M star is another set of edges. I'm just taking the union of this set of edges, and remember both of them are subsets of the edge set of the graph. So what you are getting is a subgraph of the original graph. It could be possibly disconnected. I am asking, how does any connected component of this graph look like? So there are some finite number of possibilities for each connected component. How can it look like? Shrivanti, yes, your hand is up. What kind of, yeah, okay, go on. Shrivanti.
Like, can we say that? Yeah. Yes, sir. Can we say that if we are doing M union M star, then either that the augmenting path, like neither M nor M star had an augmenting path, right, before. So
wait, we didn't. Yeah, M did not have an augmenting path. M star we are not sure. Why does M star not have an augmenting path? Oh, but yeah, because sorry, yeah, it's a max. Its size a max. Yeah, so none of them has an augmenting path. Cool. Yeah, then what?
Okay, so then either M union M star could make a larger augmenting path. That is one possibility. Like make a larger matching, because we could connect the path. I mean that one vertex within M could be connected to another vertex in M star.
But
so
is that possible? M star is a maximum size matching.
Yes, so like when we're doing the union, we have some edges, so it is possible that we we can sort of concatenate those two matching such that we have a longer matching. Like I'm saying, the possibility. We'll prove that it's not possible, but
yeah, I'm not sure what you're trying to say. So okay, let's come back to the question that I'm asking, right? How does every connected component of this graph look like, right? So there are some 10 possibilities of how it could possibly look like. What are those? That's what I'm asking. Vedant, what could you have as a connected component in this graph?
We could just have a single edge, like two vertices connected by an edge.
Okay, so you could have an edge which is present in M intersection M star.
Yes, or we could have an augmenting path.
You cannot have an augmenting path, right? Because you are talking about two matchings.
Not augmenting path, just an alternating path.
Alternating path. What else could you have? You could have isolated vertices. Right. So okay, I am talking about this graph. So let's not call it an alternating path. Let's just call it a path.
Yes.
Right. We are not talking about any specific matching.
So V is all vertices in G, right?
Yeah.
Okay.
Right. So you could have isolated vertices. You could have edges which are in both M and M star. You cannot have an isolated edge which is in one of the MIs, M or M star, because then the other guy would not be a maximum matching. What else could you have? You could have a path, right? You could have isolated vertices. What else? There is one more possibility. Vedant, your hand is up. Somaditya, your hand is also up.
So like we can also have a cycle, I think, even
Cycle. Cycle, correct. Anything else? Right? So what is the point, right? So every edge, if you look at this graph V comma M, right? So the degree of every vertex is 0 or 1. That's by definition of a matching. And similarly, if you look at the graph V comma M star, the degree of every vertex is either 0 or 1. So therefore, the degree of every vertex in this graph is going to be 0, 1 or 2 and nothing more than 2. Right? So what can you have in such a graph? You could have isolated vertices, you could have edges, isolated edges, and you could have paths, you could have cycles, nothing else. Right? Is everybody with me? Shrimanti, yes, your hand is up.
So does this seem somewhat similar to the Schroeder-Bernstein theorem where we took these cases?
Mm,
the injection from this to this. And
kind of, yeah, vaguely yes, you're right. Vaguely yes. So yeah, so that's what we did. If your injection, if your original injection from A to B is not a bijection, we kind of found augmenting paths and made it into a bijection. Yes, you're right.
Yes.
Yeah. The big difference was that that was potentially an infinite graph, and here we are not looking at infinite graphs. Okay. So that is the big difference. But yes, the idea is essentially the same. You're right. Okay. Right. So cool. Okay, so look at the graph V comma M union M star. So every vertex in this graph has degree at most 2, right? So therefore every connected component of this graph is of one of the following types.
So like, did we say that all those types are possible, or did we say that it will be one of those types only, like any connected component?
Any component will be of one of those types. That's all I'm saying. I'm not saying that you will one copy of each of those in no matter what M and M star you take. Obviously not.
Okay.
Okay. So every component must look like this five kind of, yeah, 5 categories, must fall into one of these 5 categories, whatever, 5 or 4, whatever that was. Okay. So what were the categories? Right. So category number 1, right? So isolated vertex. Category number 2, edge in M intersection M star, right? The edge is present in both M and M star, so which is why the endpoints are not connected to anything else. Okay, so third possibility is path, right? If it is a path, then obviously the edges must alternate between M and M star, with edges alternating between M and M star. Fourth possibility is a cycle, right? So cycle, obviously an even length cycle because it's a bipartite graph finally, right? So this is a subgraph of a bipartite graph, so it is also a bipartite graph, right? So even length cycle with edges alternating between M and M star, right? That's all. Actually, yeah. So let's do a little bit of reordering over here. We'll make this the fourth possibility and we'll make this the third possibility, and the reason will be kind of clear. Right. What just happened?
Can you give an example for the third one?
Yeah, we'll see an example. We'll see an example. Don't worry. Third one, you mean cycle?
Yes, yes.
Okay. Yeah, simple example. Right, so you could have, okay, let me draw something over here. Right, so let's say this is M and this is M star. Right, so you could have potentially an isolated vertex sitting somewhere. You could have an edge which is both in M as well as M star. Then what else? You could have a alternating cycle. Okay, right, and then you could have paths. Right, so you could have something like this. Right, so these are the four possibilities. This is one. This is one. This is the second possibility. This is the third possibility. And this is the fourth possibility. Okay, so let us inspect what happens in each of these connected components. So if an isolated vertex, yeah, if you have an isolated vertex, obviously it has 0 edges from M and 0 edges from M star. Remember, every edge in M union M star is going to belong to exactly one of these kind of connected components, right? So yeah, so an isolated vertex, that kind of connected component is going to contain 0 edges from M, 0 edges from M star. Right, so edge which is in M and M intersection M star, obviously that kind of a component is going to contain one edge from M, one edge from M star. Right, so even length cycle and its edges are alternating between M and M star. So obviously it will contain, right, so such, yeah, so this will contain equal number of edges from M and M star. Right, so what am I trying to prove? I am trying to prove that M is a maximum size matching. So what effectively what I'm trying to prove is that the size of M is equal to the size of M star. Right, that is my goal. And so which is why I'm saying that, okay, look at these three kinds of components. In each such component, I will have equal number of edges from M and M star. So we are only left to worry about paths. Yes, Shrimanti?
So why did you say in part 2, like possibility 2, that only one edge, the paths could have more edges common?
No, I'm talking about a connected component, right? So if some edge is if some edge is present in both M and M star, can that connected component have anything else? Right, I'm talking about connected components of this graph, V, M union M star.
Yes, sir, but it could have some more edges common, like M intersection M star.
Yeah, but each one of them is going to belong to a separate connected component. That's all I'm saying. Right, and each.
Couldn't it be a path?
Yeah, could it be a path? You tell me, right? So suppose this is an edge in M intersection M star. Okay, and I'm looking at the edge set M union M star. right? So this edge is present in both M and M star. Can this union contain another edge incident on this vertex? Right? If this guy has some edge, another edge incident on it, which is in M union M star, right? So this edge must be in either M or M star. And if this is in M, you have a contradiction because you have two edges which share an endpoint in M. If this is in M star, you have two edges which share an endpoint in M star. Does that answer your question, Srimanti?
Yes.
Yeah. So which is why if you have a edge common in M and M star, then that edge by itself will form a connected component in this graph V M union M star. Okay, that component cannot have anything else.
Sir, excuse me.
Yeah.
So why is it necessary that the isolated edges should be present in M intersection M star? It could be that it is only present in M, or it is only present in M star.
So would that not already give you a contradiction then?
So why would it be a contradiction?
Right. Okay. Why would it be a contradiction? If the edge is only present in M and not in M star, and right, so
Okay, we get an augmenting path. Yeah.
So that I can put it into category 4, right? It's a path with edges alternating between M and M star. So when we have process 4, we'll take care of it. Okay.
Okay.
Yeah, and as you said, that will form an augmenting path. You're right. Okay, so let's worry about 4. Right, so let's split this possibility 4 into 2 parts. 4a odd length paths, or rather 4a even length paths, and 4b odd length paths. Right, so 4a, the argument is again the same. It is obviously going to contain an equal number of edges from M and M star. Right, so equal number of edges from M and M star. Okay, what about odd length paths? Does somebody want to finish this argument?
Isn't that like augmenting? I guess.
Sorry?
I think you can like make an augmenting path out of this in a way.
You can make an augmenting path out of this.
Not
you are right. You are right. That path, yeah, the claim is that path itself is an augmenting path of one of the two matchings, M or M star. Vedant?
Yes, sir, that's what I was saying. That if there is an odd length path, that means the size of M star will be greater than M. So we can say that that is an augmenting path for M.
Yeah, correct. Absolutely. Okay. So yeah. So what does that mean? So look, okay, odd length path. So therefore, right. Okay. So suppose the first edge traversed first and therefore the last edge traversed by this path is in M star, let's say. So what does that mean? So then I claim that this must be an augmenting path of M. Okay. So, right. So you have this kind of a right. So this is M star again. You have this kind of a path, right? So the first edge, right? Look at the first vertex in this path, right? So this vertex does not have a pink edge incident on it. Otherwise, even that edge would be a part of the component, right? So if the first edge traversed by this path is in M star, then it means that the first vertex is unmatched under M. And by the same logic, even the last vertex is unmatched under M. Right, and then obviously edges are alternating between M and M star, right? So this is an augmenting path. So this is an augmenting path for what? Of M. And because we assume that M is a maximum size matching, yeah, sorry. So we assume that M does not have an augmenting path. So this is a contradiction. Right? And on the other hand, if first and therefore last edge traversed is in M star, is in M, this is an augmenting path of M star, same logic, right? So if you have something like this, right? So the first and the last edge in this path is traversed by M, comes from M, right? So then the first vertex of the path does not have an orange edge incident on it. Why? Because otherwise it would be a part of that component. Okay. And similarly the last vertex. So therefore this will be an augmenting path of M star. Okay, so this is a contradiction because M star is a maximum matching. Right, so what does that mean? So it means that this 4B possibility is actually just impossible. Okay, so really you have 4 categories: isolated vertices, edges in the intersection of the two matchings, even length cycles, and even length paths. That's all. Yeah, Shrimanti?
Sir, I wanted to confirm the left side indicates the person and the right side is the rooms, right?
Okay, it doesn't matter over here, but okay, fine. If that is the mental picture you want to have, sure, go on. Yes, then what?
No, sir, I wanted to confirm this. Like I was getting confused. Okay.
I mean, you're talking about a very specific application of all this theory. Okay, but yeah, okay. If you want to have that mental picture, that's fine. It's okay. Okay, so now what? Now 4B is just completely impossible. So what does that mean? Right, so no matter what category your connected component falls into, it is going to contain an equal number of edges from M and M star. And therefore what does that mean? So therefore it means that the size of M is equal to the size of M star. That is, M is also a max size matching of G. Maximum size matching in G. Shivashish Raut, your hand is up.
Sir, in the first argument of 4B, that if the first edge traversed is in M star, that part I couldn't understand. Why is it a contradiction?
If the first edge is traversed, if the first edge of that path is an M star, look at the first vertex of that path. Right? We are talking about connected components of this graph. Right? So let's go back to that graph. Yeah. So if the first edge traversed by that path is an orange edge, right? So I claim that the first vertex cannot have a pink edge incident on it. Why? Because otherwise even that edge would be a part of the connected component, and then this would not be the first edge of the path, the first vertex of the path.
Yes, sir.
Right? So the first edge cannot have a pink edge incident on it. By the same logic, even the last vertex cannot have a pink edge incident on it.
Yes.
Right? And therefore, what does it look like? So this first vertex is unmatched in the pink matching. Last vertex is unmatched in the pink matching, and you have an alternating path.
Yes, it's an augmenting path.
Okay, so that is an augmenting path.
So how is it a contradiction? Have you assumed that M does not have an augmenting path?
Yeah, look at this. M does not have an augmenting path.
Okay, sir. Yes.
Right? So what did we assume? We assumed that M does not have an augmenting path, and now we want to prove that M must be a maximum size matching on G.
Okay, sir. Got it.
Okay. Any other question? We surprisingly we have finished quite early, I would say. Yeah, so we have a lot of time for questions, and otherwise I'll try to with the next topic.
Questions.
Yes, Chinmay.
Like in the previous lecture, we started with some questions regarding the matching.
Oh,
Like
yeah, of course, yeah. So what do you want me to do exactly?
so like if you could just go to them and like this proved an algorithm, right, to get a matching of maximum size, but then how does it answer those questions?
Achha, those questions. Okay. So you want me to open the last lecture's notes?
Yes, sir, if possible.
Okay, sure, why not? Achha. Okay, yeah, cool. So where should I? Yeah, these questions you're talking about?
Yes, sir. Yes, sir.
Okay. Right. So now, yeah. So what is your question? What did you want to say? I still don't get it.
So I meant that we will start from some student who has a room preference, at least one, and we'll do this algorithm, and then we'll get a maximum size matching, right?
Correct.
So if it has X students, like if it has X like that, then we can say that only like X is the maximum number, irrespective of which student we started from.
Correct. Yes, you're right.
So if X is all students, then first question will be true, otherwise false. And like, what about the third question? Like, how will we expand?
I'm coming to the third question now. I'm coming to the third question. Right. That is the next topic of discussion. Okay, Raman.
Sir, isn't the third question what we are doing? I mean, we're literally generating the algorithm to create a maximum matching.
No, third question says, suppose you want to modify the graph so that you get a better matching.
Okay,
Where
sir.
should you add edges?
Okay, sir.
Right. So which students should you request to expand their choice, or which room should you improve so that hopefully more students prefer them? Okay, that is the plan. Ramanuj, your hand is still up. Is there anything else you wanted to ask?
So instead of saying like which rooms we should renovate, that's kind of like okay, but like isn't saying like how many maximum edges we should add to the graph such that we can create a maximum match. How many minimum edges we should add to the graph such that we can create a maximum matching, like a better, more easier.
Can people hear Ramanuj properly? I mean,
Sir, I think he's saying that instead of putting it this way, should we put it this way, that what are the minimum number of edges that we need to add to a graph so that we can create a can match everybody?
That's not the way I'm trying to put it. All I'm saying is, can we kind of hold some vertices responsible for the graph not have a maximum matching? Okay, and I'll make it concrete now. I'll write a statement I'll very soon write a statement of a theorem, and I'll make it concrete. Shrimanti?
Sir, can we say that we'll add edges only when we are able to connect two maximum size matchings together, so that we can concatenate them, or maybe not concatenate them, but concatenate a subset of them, so that in total it becomes the entire graph gets connected.
I am not sure I understand your comment. So could we do it this way? Let's understand what that lemma is trying to say, and then let's see whether that answers this question number 3. Okay, and then if you have objections, we'll take it up. Vedant?
Sir, I had a general doubt. Like, when we start with some edge, like first we take an edge when we are trying to find a matching, then we'll apply the augmenting path algorithm multiple times, and finally we'll land up at some maximum matching, right? So, taking any edge will not give us the maximum matching, right? Only a particular subset of edges will give us.
No, that's the claim. Start with any edge. That is going to give you a maximum matching, possibly different matching depending on where you what you started out with.
Okay, but sir, when we take some vertex, like when we take some student, for example, Rajat, then Rajat will be in the the students list in our matching forever, right?
Yeah,
Like,
so once somebody gets a room, they get a room forever. Possibly it's a different room, right?
okay.
But we are not throwing them out of room. We are not deallocating a room to them. Never.
So every student will be a part of a possible maximum matching. That's what you're
Provided they
saying.
have a non-empty set of
Yes.
room.
Okay.
Okay, if somebody has an empty set of room, they just don't like the hostels, well, we'll say stay off campus.
Oh, okay, sir.
Okay. Okay, fine. Chalo. So let's come to the other. Why am I not able to open anything? This is weird.
So what Ramanuj observations?
Sorry?
Sir, you said that Ramanuj had an observation. I wasn't able to understand it properly.
So the observation was if some student has a non-empty set of rooms which he or she prefers, then we can always construct a maximum matching in which this student is matched. Okay, that's the claim. Right? How do you do that? You assign some arbitrary room to the student, any of the rooms which he or she prefers, and then you go on augmenting until you cannot find any more augmentation. And the property that we are maintaining is if some student is assigned a room, right? So they remained, we continue to assign them some room, possibly different room over time. We change their room possibly over time, but we never throw them out of the hostel. Okay?
Okay, thank you.
Yeah. This is lecture 12, no? Okay, cool.
Sir, excuse me.
Yeah.
Sir, is it correct to assume this the case of hostlers and rooms to understand matching, sir? Because the existence of matching has nothing got to do with bipartite graphs.
Yes, you're right. The existence of matching has nothing to do with bipartite graphs. Matchings are very well defined even in arbitrary graphs. But in case of arbitrary graphs, you don't have so much of structure, right? So you can still find a maximum size matching in an arbitrary graph efficiently, but that algorithm is kind of much more complicated than this.
Okay.
Okay, so it's kind of hard.
Okay.
Right, so there you'll have to look at something called I think the original paper which gave that algorithm, it called some those specific structures as blossoms or something for whatever reason. Yeah, so you have to look at more complicated things, right? So for example, right, so good point. So let's quickly discuss that before we go ahead. If you have a non-bipartite graph, right, so let me draw
So create an odd length cycle with a leaf extending from one edge.
Good point. Right, so if you have an odd length cycle with a leaf, and let's say my current matching is this, right? So now there is no augmenting path.
No, sir, there is the upper two.
Sorry.
The leaf is an augmenting.
Oh, sorry, the leaf. Okay, okay. So how do we fix that?
So
cool. Yeah.
Make that also as a matching.
Yeah. Okay. Yeah. Hold on. Okay. Wait. So I believe this does not have an augmenting path.
No, sir. I think we can do it like this. Sir, we match the edges of the leaf, vertices of the leaf.
Wait. What am I trying to construct? I'm trying to construct a non-maximum matching which also does not have an augmenting path.
Yes, sir.
Right. So this matching is of size 2, right? And I have a better matching, which is this. But the red matching does not have an augmenting path.
So it does, right?
Sir, it does have a red augmenting path.
So the three edges.
What is an augmenting
green,
path? Red matching. Oh
green,
yeah.
Yeah.
Okay, fine. What is a good example then? Yeah.
No, sir. I was just saying that there exists a maximum matching even for the case of non-bipartite graph.
Yeah, it makes sense.
As green is here.
Yeah.
So why are we always considering bipartite graphs as
So that is the point. So the point is that this characterization of whether a matching is a maximum size matching on the basis of whether there is an augmenting path or not, that is true for bipartite graphs and did not be true for general graphs, which is why we just focused on bipartite graphs. For general graphs, there is a more complicated algorithm.
Okay.
Okay. Yeah. What could be an example? Yeah. Okay.
So I guess if we have a hexagon and a leaf, then maybe.
Hexagon and leaf would make it a bipartite graph.
Yeah, it is a bipartite.
Right.
A non-bipartite graph
right.
must constrain an odd length cycle.
Yeah.
Sorry?
Saying a non-bipartite graph must contain an odd
must
length
contain an odd length cycle. Yeah, cool. Yeah, that is true. Okay, so let me quickly try. If I don't get it, then we'll do that in the next lecture quickly maybe. Right. So this red matching, and then let's say you have another leaf.
Sir, I think I have an example.
Okay, cool.
So take a square, add a diagonal, and like add and take the bottom two vertices and have a leaf, attach a leaf to them.
Now
And
what
now
is
take
your
the opposite, like take the left and right edge of the square. I think AC and BD. I think that works.
So AC and BD is your matching.
Yeah.
Okay. Now this does not have an augmenting path, is it?
This
Right.
does not.
It does, right?
Oh, right. It does.
ECABDF.
Yeah.
E what? Say that again.
ECABDF. BDF.
BDF. Yeah.
Right. It does.
Yeah. Yeah. That's true. Yeah. Okay. Fine. Let's not spend too much time on this. I'll find an example. Should not be hard, but I'll take some couple of minutes at least.
Sir, I had a doubt.
Sir, one.
Yeah.
Sir, augmenting path need not be maximal, right? Like it can be like just have one edge of M in it.
Yeah, I don't care about the length of the augmenting path.
Yes,
as
sir.
soon as I find an augmenting path, I have an improvement of 1 in the maximum.
Why cannot a maximum matching have a augmenting path?
Right, because if you XOR the matching with the augmenting path, you get a better matching. Right?
No, like,
Sir,
take a fully connected bipartite graph. It will have a augmenting path, right?
Fully connected bipartite graph, and what is your matching?
So like label the vertex ones. So now if AD, BE and CF are matched, sir, isn't AEC augmenting? Sir,
is it what an augmenting path?
Sir, AEBF.
AEBF.
Yes, sir.
What did we say? An augmenting path must start from an unmatched vertex. No?
Yeah, F is matched to C and A is matched to D.
Yeah, as soon as you have a perfect matching, you just cannot have an augmenting path.
Oh, sir, why isn't this an augmenting path?
No, what is the definition of an augmenting path? Right?
Sir, it should be alternate. It should be alternate, and last edge should not be a part of.
So that's the mistake I had made in the last lecture, and I corrected it today. Okay. I said that an alternating path is called an augmenting path if the first and the last vertices are unmatched. That is the one big mistake I had made in the last lecture. I'll fix those last lecture notes and re-upload them.
Right, sir.
Okay.
Right.
Yeah, sorry. Yeah, that was my mistake. Yeah, somebody was saying something. Also, Shrimanti.
So, like I was creating, like I was thinking every time we were doing this proof, I was thinking of that room matching example, but now I'm not able to figure what exactly were we using of the bipartition in the proof of the theorem, the last theorem.
What exactly were we using about the bipartition? Right. So here, right. So you're talking about this proof, right?
Yes.
Yeah. So look at this. If your graph is not bipartite, you could have odd length cycles also.
Okay. Got it.
Okay. Yeah. So that kind of creates some more mess in case of non-bipartite graphs. Okay, Shrimanti, yes, your hand is up.
Sir, can you draw that odd length pentagon once? Like I couldn't understand which two vertices you considered for the augmenting path. New augmenting path.
I couldn't construct a proper example. That is the issue. Right. So this was something I had. Yeah, I couldn't really construct a concrete counterexample. Maybe I'm close, but yeah, okay. So if I
What
can't
was
see-
the issue? Can you
Sorry?
what was the issue? Can you explain once?
No, I was trying to construct a non-bipartite graph in which matching is not a maximum matching, but still it does not have an augmenting path. That's what I was trying to construct. Okay.
Yes, so like when we draw two edges here for the matching, which edge is which edge is belonging to which set, which V1 or which V2, or it does not matter.
It's not a bipartite graph. What are V1 and V2? If your graph itself is not bipartite, what V1, V2 are you talking about?
Yes, sir, but then how are we like matching the third vertex? Like how do we construct the augmenting path then? We were taking one from V1 and another from V2.
See, Shrimanti, first of all, I'm saying that in case of a non-bipartite graph, all that we said so far might not even be true. You could have a non-maximum matching which does not have an augmenting path. Okay.
Yes, sir, but in this example, like what was the issue we were running into? If we take two edges,
Which two edges do you want me to take? Let's call this something A, B, C, D, E, F, G. Yeah, tell me what edges should I take?
say we take BC and GF.
BC and GF. Okay, fine. Then this ED is an augmenting path.
Okay, if we remove ED, the previous one, then
Sorry?
if we remove ED,
Oh, you
He's
remove
asking
it.
you to draw a graph in which ED is not present.
Acha, so if you remove ED, then A, B, C, D is an augmenting path.
Sir, actually,
Yeah.
sir, like thought about it, I think you always have an augmenting, but you don't have an augmenting path even for non-bipartite case because a proof completely holds. You can prove the even cycle thing without using bipartiteness.
Sorry, I couldn't understand it. What is it?
So even in non-bipartite case, I think you can prove that if it's a maximum matching, there is no augmenting path. And yeah.
No, in a one way it is true. In the maximum, if a maximum
Sorry.
then it does not have an augmenting path. That is
Sorry,
true.
I meant the opposite. If there is no augmenting part, then it must be maximum. Because if we go back to our proof, the only time we used bipartiteness was in proving even cycle portion.
Correct.
And
So,
you can actually, I think you can prove it without using bipartiteness because of how the edges are connected.
How do you do that?
I think it would be complicated though, right? Because, for example, you have alternating color edges, but now you can't have alternating color edges.
Because exactly. Because if you have an odd cycle and then two edges must be part of the same matching, and if they're part of the same matching,
Yeah, I think you have a point. I think you have a point. Acha. Oh, yeah. You have a point. Yeah, I think all this will wait. Yeah, you are right. Sorry, my bad. Yeah, you are right. All this will hold. The issue will arise when you are actually trying to find an augmenting path. Right. So if you go to although we have not seen the algorithm to find an augmenting path, the problem really lies in that algorithm, right? So if your graph is kind of bipartite, then the algorithm is much simpler. Okay, the algorithm which finds an augmenting path, it's fairly straightforward. Although we haven't looked at it. Yeah, if your graph is non-bipartite, it gets into more complications. Yeah, so you're right. Yeah, so I think wait. So yeah, I'm willing to say that if this also holds for general graphs. Sounds okay. Yeah, but okay. Remember the next thing that we are going to prove, another relation between the existence of maximum matching and something else, some other properties of the graph, that definitely does not hold for non-bipartite graphs, which is why I just focused on bipartite graphs. Okay. Yeah, we have 5 minutes, but I don't. Okay, fine. So let's do that. Let's maybe pose a question for you to think on, and then end the lecture. Right. So let us draw again the same scenario. Let's draw another bipartite graph. You have students, you have rooms, and so on as before, right? So let's draw some edges. Okay. Okay, so this is my bipartite graph. These are the students, these are the rooms. So let's call them something: S1, S2, S3, S4, S5, R1, R2, R3, R4, R5. Maybe let's add one more edge, couple of more edges. Now, can you stare at this picture for a minute or so and tell whether this graph has a bipartite, whether this graph has a perfect matching or not?
Sir, I think it doesn't.
Okay, why, Arun?
Sir, because 3 of the vertices are matching 2 of the rooms. 3 of the students
Which
are
three?
matching.
Which 3 vertices?
S1, S2, S3
Yeah, S1, S2, S3. Yeah, so yeah, yes, you're
are matched to R1 and R2, so it cannot be a perfect.
are adjacent to. Don't say they're matched to. They're adjacent to only R1 and R2.
Yeah,
Yeah.
they are adjacent to
Yes.
only.
So look at these 3 students, S1, S2, and S3. So these 3 students are fighting for 2 rooms. Okay, so well, you need not have all pairs of edges between these students, but still the point is still the same, that right. So if you kind of take the neighborhood of this set of students, its size, the size of the neighborhood, is strictly smaller than the size of this set of students, right? And as soon as you have this kind of a structure in your graph, bipartite graph, the graph is not going to have a perfect matching, right? If you have more number of students fighting for a smaller set of rooms, you just cannot assign rooms to everybody. So now, right, so what observation? Large set of students fighting for small set of rooms implies not all students can be matched. Students can be matched. So the question we are trying to answer is the following. Suppose you don't have this kind of a structure. Okay, so the question we are trying to answer is the following. Suppose that the matching which matches the maximum number of students does not match all students, right? Is this the only thing responsible for that? Right, so what we'll say is, if for all subset S subset of set of students, we have the size of S is less than or equal to size of so-called neighborhood of S, right? So this is the set of rooms preferred by at least one student in S, right? So here it is violated. Here, if this is your S, then this is your N of S, and then this property is violated. But then I'm saying, suppose that this property is satisfied. If for all S subset of students this property is satisfied, does this imply that there exists a room, right? There exists a room assignment for every student. Which allocates rooms to every student. Room to all students. right? So this is what we'll investigate in the next class. All right, so we are already over time. Chalo, so let's not take questions. Let's take questions in the beginning of the next class, if any. Chalo, lecture khatam. That's all for today.